Having discussed about the Maxwell's relation, let's now see how to memorize these relations or how to obtain these relations within minimum time. So let's recall the thermodynamic potentials. That should be always with you. So you know the natural variables are V and S. So the first Maxwell relation will be obtained from the definition of U and its natural variables. So that is dou V. You see how I am writing, and you try to relate it. Dou V with respect to dou S. Dou V with respect to dou S at constant P. At constant P, that's equal to dou T with respect to dou P with respect to dou P at constant Es. This was the first equation which we obtained it from exact nature of du. Now the second one, H Ps, natural variables were P and S. So we obtained the second equation, which was written as dou P with respect to dou S. Dou P with respect to dou S. So you can see this one. See V and S going on comparing the parent thermodynamic function or thermodynamic potential and the Maxwell's equations. So that is equal to minus dou T by dou V. Dou T by dou V. And you have to keep the constants. Here I will be keeping V as constant. Here I will be keeping S as constant. Now the third one is A, Helmholtz free energy, AVT. By the time I think you should be familiar. AVT. So what will be the equation? Try writing dou V with respect to dou T with respect to dou T at constant pressure. That's equal to minus dou S with respect to dou P with respect to dou P at constant T. And the fourth one is GPT. That's dou P with respect to dou T with respect to dou T at constant V is equal to dou S with respect to dou V with the constant T. So these are the equations. So let me call it as first Maxwell's equation. In an order, I am just naming it. Second Maxwell's equation, third Maxwell's equation, and fourth Maxwell's equation. So several ways you can memorize how to write it. Just discuss its main features or salient features, which will help you to always verify whether a given equation is correct. Okay. One thing you have to note that just you check the cross variables. Just check the cross variables in all the four equations. You will see there is some notable feature. What is the common feature? See, cross variable means here V, here P. Here, see in the bracket I am telling S, here T. Can you see what are the cross variables? It's PV and TS. Did you note it? Then in the second equation also you note it. Okay, PV, here it is P, here it is V, and here it is S, here it is T. So the cross variables are PV and TS again. Okay, next equation, PV, P here, V here, that's all, and T and S here. See, again ST, PV and TS. Right. In the last or fourth equation also, it is PV and again TS. It's not quite easy, and is not an interesting feature? PV and TS, and already we have defined that P and V forms a conjugate pair and T and S forms a conjugate pair. Not only that, the product PV and the product TS will always have the dimensions of energy. right? So that is one notable feature of all Maxwell's relations, the cross products. Okay, the cross products should be always either PV and or TS. So it's quite easy for you to check whether a given relation has been given incorrect. Always check this one. This should be without any compromise. This particular feature will be there in all Maxwell's relations. That is one thing which will help you to write the equation even if you don't remember all other steps. One thing. Now let me just rub it off. Let me rub off the thing. Okay, sorry, yeah, everything will be gone. Yeah, let's retain it as such. Okay, otherwise it will be difficult. Okay, fine. Now another thing. So you obtained the cross derivatives. You know how to pair it up. Now the next thing. So you have to decide which parameter will be kept as a constant in the partial derivative. So here, you know, in the first thing it is P here, and here it is S. See, how do you decide it? You see the variable which is kept as a constant will be the conjugate variable of the numerator. That is the notable feature. I am writing it here. The conjugate, okay, conjugate, you know, P and B, T and S, conjugate variable of the numerator, will be maintained, or I can say will be kept as constant. So it's quite easy now. You need not worry about it. So it is V, so it is P here. Here it is T, you can automatically write it is S. So now look at all other equations. See, here it is P in the second equation, P here. So here it is V, which is maintained constant. T here, the conjugate is S, maintained as a constant. Here again V and P, here S and T. Quite easy, no? P and V, S and T. Did you note that one? Okay. So all the conjugate variables are related that way also. That is one thing. Now what is the trouble with us? What is the problem? Only problem. You know that two equations, two of the Maxwell's relations are having a negative sign and two of them are positive. How to recall it? If it is not written in order, because you know very often this particular side will not be there, right? So this one will not be there, and these equations may be given in any order. So how do you remember it? That also, let me tell you a technique. Okay, so the thing, you can see that in two of these equations, there will be P and T. There will be P and T coming as numerator and denominator. P and T coming as numerator and denominator on the same side. Look at those equations. One is the first equation. Here T is there, here P is there. So T by P, either P by T or T by P, because I told you not only these four equations, their reciprocal relations are also valid Maxwell's equations. Okay, so T by P comes, or P and T are coming as numerator and denominator, or denominator and numerator on the same side. So which other? So equation number 1 okay, suits our checking. So here what is that? P by S, T by V, no. V by T, S by P, no. Okay, then P by T, yeah, here fourth equation you can see. Here it is P by T coming to the left side, both okay, on the same side, P by T. So either P by T or T by P equations, whichever Maxwell's equation having P by T or T by P. Okay, so they will be positive. That is another okay, simple technique to memorize. This actually we are like I told you that we are analyzing the equation for its symmetry, what is its property. These are our aim is to just memorize or recall it within minimum time. Okay, so that is another thing. Now let me tell you another way of easily writing all these equations. That also can be shown, how to easily write all these equations. See, just you remember this one. You just write P by T equal to, what should be equal to? P by T equal to, it should be its cross derivative should be always PV and TSO. So I should write this one should be equal to what? S by V. Just write like this. P by T equal to S by V. This is another technique of writing Maxwell's relation directly. P by T equal to S by V, right? And the reason why I have written P by T equal to S by V, so that on cross multiplying this one, see, you get TS and you get here as what? PV, right? Now, you can just see P by T equal to S by V. Which is that equation? This is the equation, see. This is the equation. And you know what to do. Just you add dou P, dou T, dou S, dou V, like that you do. And since P and T are on the same side, that will be positive. And now you can keep the variable. Numerator is P, so the variable here is what? Sorry, the constant here will be V. Here, numerator here is S, so it will be what? T. So didn't you get the fourth equation? Okay. Now what you can do? You can just make shifts. You can make shifts correspondingly. Always maintain that the cross derivatives are, products are always P, V and T. Okay. So what I'm doing is that, let me take this S to this side and T to this side. Okay. So what is that? P by S. P by S. So what will be the other thing? It will be T by V. Check it. So what I will do now next, dou P, dou S, dou T, dou V. These are all fancy techniques. Okay. Then you have to keep the things as constants. P is in the numerator, so V will be constant. T is in the numerator, so S will be constant. Now you have to decide the sign, whether plus or minus. See, is there any P by T term anywhere? No, no P by T. Here it is P by S and here it is T by V. So this equation should be negative. And which is that equation? And that is the second equation. See, dou P by dou S. See, dou P by dou S, that equation. Is it clear? Okay. Now you need to have two more equations. Which are that two more equations? Okay. So look at this equation. Yeah. See, this one. Equation number 1. Equation number dou V by dou S equal to dou T by dou P. How do you get it? Just invert this equation. Invert this equation. See, what is that? Inverting this equation you will give. Okay, you write T by P equal to, is not? T by P should be equal to what? It should be equal to V by S, is not? Always follow that the cross products are giving TS and PV, so it's quite easy. So T, can you see that? V by S is equal to T by P. You can check it here. T by P, V by S. Now you do the same technique. Dou V, dou S. Then T and P are on the same side, so this equation should be positive. Then you write what are the things which is kept as constant. It is T in the numerator, so it will be what? Okay, yes. Here V is in the numerator, so that will be P. Okay, and you can see that that's, and the left and right can always change. And the same manner, you can invert this particular equation and write the corresponding variables. Okay, see that you do not okay, just to retain this thing as such. You have to write this things which are kept as constant only after writing its equation, because these things are corresponding to the conjugate variable of the numerator. So when you invert it, see that you do not maintain this V as V and S as S. So automatically it will be getting T and see P, T and P. That you can just check it with the what do you say, the third equation. I think by the time it's not a problem, not at all a problem for you to write down even directly. Okay, all the four Maxwell's relations. Okay, so a word of caution for you. See that whenever it is asked in your university examinations, you try to derive them as what we have done in our previous video. Like start from the definition, then systematically write down its property of analytic functions, that mixed derivatives are having some symmetry. Then state that these all the four functions, all the four thermodynamic potentials are state functions, and hence their total differential will be exact. And for exact differentials, dou M by dou X, okay, that relationship is correct. And from that relationship, see that you arrive at the Maxwell's relations. Even though you are able to memorize it by the time and reproduce it, always after doing in the straightforward manner, please cross-check all those properties or memory aids that I have discussed so far to verify whether the equations derived are perfect or without any error. Okay. Now, see, let me discuss about quickly about what are the significance, why we are so bothered, why we are spending so much time on discussing these 4 equations. There is a lot of things which makes them significant. So we'll discuss the uses of Maxwell's relations, or what are the significance of Maxwell's relations. Now, to be quick, it provides the foremost one. It provides a relationship between different thermodynamic variables. Each of the 4 Maxwell's relation relates the various thermodynamic variables. Which are thermodynamic variables? It relates pressure, volume, temperature, and entropy. And that's interesting thing. Okay, PV and TS are related in all the 4 thermodynamic Maxwell's equations. You can see that it's relating PV and TS. See, TVPS. So it's only relating PV and TS. But how do you get those equations? They are obtained from the Maxwell's, they are obtained from the thermodynamic potentials or characteristic functions. That is why here it is from the definition of thermodynamic potential it has been stated. Okay, that is one thing. So provides mutual relationship between different thermodynamic variables. Actually, they are relating the partial derivative of these thermodynamic variables. One thing. Second one, to determine quantities which are hard to measure directly in terms of easily accessible ones. That is yet another significance of Maxwell's relation, or what is the importance of Maxwell's relations. Just look at these 4 variables. Pressure, can you measure pressure of a system quite easily? Is it not an experimentally measurable, controllable variable? Yeah, of course. Why? Because there are pressure gauges. Like we have discussed, sphygmomanometer to measure your blood pressure. You have barometer to measure the atmospheric pressure. So you can always use some kind of proper pressure gauges to measure pressure. Okay, so that is not an difficult one. Volume. Can't you measure the volume of a system very easily? Yeah, you need to have only a calibrated chamber or a calibrated cylinder. Okay, a calibrated cylinder. In the case of gas, it doesn't matter because it will be occupying the volume of the entire container. In the case of liquid, okay, if you have a calibrated beaker, okay, or pipetting burettes, all these things, they will be giving you what is the volume of the particular system. Now, so that is also experimentally accessible and easily measurable. Temperature, temperature is yet another variable which can be quite easily measured. You can use the proper type of thermometer. Depending on the temperature range, you can use mercury thermometer, or you can use some thermocouple based thermometers. There are several kind of thermometers. Okay, so out of these 4 variables, these 3 are easily accessible and experimentally controllable. But the 4th one is still a mystery, like we are discussed. Okay, we could even just define what we call as entropy. But I told you, or we have seen that there is some sort of some vagueness or abstractness still related with entropy, and we have seen that it is quite difficult to directly measure the absolute entropy of a system. Okay, but instead we are measuring the change in entropy, and hence, in all the 4 Maxwell's relations there will be a ds or dou-s. Dou-s is there in all the 4 Maxwell relations because it will all will be having PV and TS, either in the numerator or in the denominator on either side, right? So ds will be an integral part in all the 4 thermodynamic Maxwell's equations. So in terms of under different conditions, in terms of the directly measurable variables, namely PV and T, the difficult to measure or hard to measure quantity like entropy can be very easily measured. So like you have got a P by T is equal to S by P. This is the basic structure, right? I'm not writing dou P, S by V, right? Okay, I'm not writing the dou and all. So you know that if P is known or dou P is known, dou T is known and dou V is known, can't you calculate dou S theoretically? Okay, yeah, that is mathematically possible. And if 3 of them are known, the 4th one can be measured, and that is actually the supreme significance of Maxwell relation. Even though I have put up it in the second thing, that's why Maxwell relations assume much importance. Now, third point. To provide information regarding the statistical interpretation of entropy. What is the statistical interpretation of entropy? Just recall the famous Boltzmann's equation, S equal to KB log omega. Okay, where I told you omega represents the number of microstates that is accessible to the system. We will discuss more about these concepts in the next module, the remaining last module that we are yet to see. But anyway, statistically we are able to measure absolute entropy, and we are able to say that entropy of a system will be equal to 0 at absolute 0, T equal to 0 Kelvin. So S of the system tends to 0 when temperature tends to absolute 0. Actually, this is what is known as the third law of thermodynamics, which is not directly mentioned in your syllabus, but it's good that you understand. Third law of thermodynamics states that in the limit temperature tending to 0 Kelvin, the entropy of the system will be just tending to 0 joule per Kelvin, and that denotes perfect order. Okay, this is also known as the Nernst theorem. Nernst, Nernst theorem in thermodynamics. I just mentioned it. So to provide information regarding the statistical interpretation of entropy means this Maxwell's relations will finally support the interpretation of entropy using statistical mechanics. How it is done? For example, you consider the fourth Maxwell's relation. What is the fourth Maxwell's relation? So that was dou V by dou T. Dou V by dou T at constant pressure, that is equal to minus dou S by dou P minus dou S by dou P. What will be the constant here? S is here in the numerator, so it should be T. There is no doubt, I think, by the time. Okay, so you can now go on checking whether the properties we have discussed are true everywhere. Now see what is dou. Let's try to understand the meaning of these equations. Dou V by dou T. What is the meaning of dou V by dou T? Try to visualize it. Okay, suppose that we are talking about you are talking about a substance whose volume is V. Okay, at some instant its volume is V. Okay, it can be a solid substance, you see, and like a block of a material. Remember one thing, that the Maxwell's relations are applicable for, that I should mention. Maxwell's relations are applicable to all types of solids, liquids and gases under all conditions of pressure, volume and temperature. So it is a universal set of equations applicable for solids, liquids and gases. Okay, so that's why I'm just not taking a gas alone. I'm discussing any object. You take, for example, a block of copper. Okay, some example, a block of metal or something. Now, how do you visualize this dou V by dou T? What's the meaning of dou V by dou T? Dou V means change in volume. Dou T means what? Change in temperature. So what is the meaning of dou V by dou T? That is change in volume of a substance with respect to the change in temperature. It means that how much change will be there in the volume for a given change in temperature. But there is a condition. What should be maintained as a constant? Pressure should be maintained as a constant. So this one can be just understood as the expansivity of the material. Can you see? Expansivity of the material. What is my expansivity? You heat this particular metal block, for example. When you heat this metal block, metals tend to expand. Okay, so can't you just imagine that there is a slight increase in the volume of the metal block? It will be expanding to all the sides, you imagine, and so the volume will be changing. So the change in volume is dV, right? And the change in temperature is dt. So you take dV by dt, right? So dV will be positive and dt will be positive. Okay, and you have a condition that you keep the pressure constant. You are doing it under atmospheric pressure, so it is open to atmospheric pressure. So I can say the left side equation represents the isothermal increase of pressure. The isobaric increase of temperature, right? And so this quantity is what is known as the expansivity. So if the substance is having positive expansivity, means if this side is positive, if this side is surely positive, it need not happen always like that. There are substances whose expansivity is negative. So, but if the substance is having positive expansivity, then let us say what is the negative sign on the other side representing. Okay, here what is minus dou S by dou P at T? Minus dou S by dou P at T. What does it mean? Dou S by dou P means what, that dot T at T means isothermal, under isothermal conditions. Okay, the isothermal increase of pressure. You increase the pressure of the substance under constant temperature, then what should happen to the entropy? Okay, if you increase the pressure, okay, means if you are increasing the pressure, means the denominator is increased under isothermal conditions. That is the meaning of isothermal increase of pressure will result in a decrease of entropy. That is why there is a minus here. You increase the pressure, entropy will be getting decreased. That is why the negative sign here. So it will result in isothermal increase of the pressure of such a substance having positive expansivity will be resulting in a reduction in the entropy. Reduction in the entropy means, entropy we have been regarding as a measure of the randomness or the disorder. Reduction in entropy then corresponds to what is known as what? More order. Means the molecules will be in a more ordered state under this situation. And this particular fact has been established or proved by using the statistical mechanics or statistical interpretation of entropy starting from this equation. And there are several cases where this statistical interpretation have been proved by Maxwell relation. This is one particular example that we usually come across. Okay, now fourth one already we have discussed, and finally fifth one. It can be used to solve any thermodynamic problem. There are a large number of thermodynamic problems which has to be solved theoretically. Theoretically, you have to explain a number of observations. Okay, empirical results you have to explain it by using theoretical background. So these equations will be of use to us in explaining a number of thermodynamic problems. And of course, you will have to use the first and second laws of thermodynamics. Okay, like du is equal to du is equal to d bar q plus is not right d bar w, whatever it is, and you can change its forms in several ways. And also second law is the law of entropy, right? Okay, that is d bar q by t is equal to ds, whatever it is, different forms you can write. Along with these equations, you can use the four Maxwell relation and you will be able to explain most of the thermodynamic problems that we are usually coming across. So we'll be just discussing the applications of Maxwell relation. You will see where we are deriving a number of equations starting from Maxwell's equations. Okay, so that's about the use or significance of Maxwell's relations. Okay, now before we end up the session, let me introduce one more thing, that is a textbook mnemonic to memorize Maxwell relations, which is nothing but it's known as commonly as the conic bone diagram. Conic bone diagram. Remember, it's not that much relevant. Okay, conic bone diagram. It is a bone is Max bone. You heard of Max bone? Max bone is one of the famous physicist. It was a technique. Okay, it was a technique that is named after Max Born, and it was a technique that was popularized by the students of Max Born. So to respect his teacher or their teacher, this Max Born students actually popularized a particular diagram. What you see here, it's a square diagram. What you see on the screen, and it was actually Koenig was the person who first published it. It was popularized by the students of Max Born, the famous scientist, and it was published by Koenig, and hence now it is known in literature as conic bone diagram. Just remember, this conic bone diagram is just a mnemonic device. What is meant by mnemonic device? Whenever you have to memorize some very important concepts in science or anywhere, you can depend upon some memory technique, like the 7 colors of white light. You remember how? Right from your beginning, you have been using the mnemonic VibGeor, right? So by just recalling VibGeor, you will be able to say about what all the white light wavelengths in order. So VibGeor is a mnemonic. It's a memory aid. It's a magical formula. So similarly, the conic bone diagram is used commonly, universally as a technique to remember Maxwell's relations or the the four characteristic functions with its natural variables. I think by the time you have already mastered all those equations, I think, okay, because we have been repeating things in different ways with a just little bit of investment of time. By the time you must have just memorize the equation. But let me introduce what actually is the conic bone diagram. If all other techniques that I have already mentioned fails, at least there should be a life buoy, at least there should be a just life jacket, and that life jacket is a standard conic bone diagram, also known as, or the square diagram is also known as the Watt-Woos diagram. That's another general name, Watt-Woos diagram. And why it is known as Watt-Woos diagram? When you look at the square here, you can see some labels here, VAT. Can you see VAT here on the top? And if you read it bottom, read it like this, bottom, and you read it like this, that is Watt, and you read it downwards in the column, that will be VUS. So it is WUS. So it is Watt-Woos diagram. These are all memory techniques, that's all. Okay, remember, so conic bone diagram is a mnemonic device, mnemonic technique used to remember or recall the four characteristic functions. What is meant by characteristic function? Characteristic function is other name for thermodynamic potentials, namely U, H, A and G. These are the characteristic functions of thermodynamic potential. And the associated Maxwell's relations. Associated Maxwell relations, because we have defined the four Maxwell relations from the definitions of UH, A and G. So if you are able to recall these things, you will be able to write the Maxwell relation. That is a technique. Now what is the technique? You can see that. See, just look at the diagram, and I think the diagram itself will tell you what how it is used. Watt, you look at the the center of the square, not center of the square, please, the center of the sides of the square. See, this side, the top side of the square, A is written. A is one of the potential. Then on the other side here, G is written. Okay, Helmholtz free energy, Gibbs free energy, middle. Then H is written, another thermodynamic potential, and U is written. So in this diagram, conic bone diagram, the four sides of the square, okay, will be marked with the four characteristic function in a particular order. Okay, so in order to remember that order, you can just write VAT, Watt, and VUS, WUS, Watt, WUS. Okay, if you are able to write Watt-Woos, it's because it's a rhyming word, right? Okay, every student likes rhymes. There is some tune. Watt-Woos. So what are things? These things have come. Now, if you have written this one, there are two more potentials remaining. What are that? They are H and G. Now let's see how to write it. Okay, different ways you can understand. Now see that it's T. As I told you, see the cross derivative or cross diagonals, the diagonals, they will be always TS and PV. So it's quite easy, right? So it is what? ST. Now if it is so, what should be here? What should be here? Pardon me for the line. Okay, so it should be P. It's PV TS. Can you see that? Conjugate variables are cross variables. Okay, now quite easy. See what of this one? See what is the relation of V and T for A? Because we have seen that A is a function of Vt. V and T were the natural variables. Similarly, what is the relation? Sorry, what is the relation of V and S with U? Because U was a function of V and S. UV, UVS, VS. I told you. Okay, AVT. I told you. Now again, so if that is the case, we are writing on the two corners the natural variables of the thermodynamic potential, which is written at the middle of the side. Okay, at the center of the side. So you can quite easily. So what should come here? So you look at here it is T, here it is P. P and T, these are the natural variable of which thermodynamic potential? No doubt that is G. because you are familiar that G is a function of PT from our previous experience, GPT. Now what is remaining? So what is remaining is H. Okay, that also is clear because H is a function of P and S. It's not quite easy. So once you write this equation, then you can or if you recall this diagram, if you draw this diagram correctly with these arrows, be careful about these arrows. See that the arrows are running to the top. Okay, these arrows have something to do with the positive and negative signs in your Maxwell's relations. Now once you write it like this, let's see how to write the differential. So you can write du equal to, see, du equal to, from this equation, du, I'm writing about this one, left side, du equal to, like it's this one. No, what you have to do is that here v is there, du, u has got v and s. So what you do is that you have to write one equation like this and another equation like this. Okay, so what I'll be writing minus p dv, just see how I'm getting, plus t ds. This equation is familiar to you by the time, but how it is recalled from the Maxwell's diagram, it is a minus p dv. Okay, minus p dv, v is the variable, so I am writing dv. Okay, s is the natural variable, so I am writing ds, the same manner. Right, now why it is minus p dv? Because here it is v here, but the arrow is running top. Okay, so you can see that it's dv, but the arrow is running to the top. So in that case I have to take what? The minus sign. Right, or you remember that p and as I mentioned, p and which one? P and s are always what? Negative. And v and t are always what? Positive when they are used as the coefficient. These are the coefficients. That is one thing. Now similarly you can write all other equations. So you just try to write all other equations from the thing. dh, for example, dh, the bottom one, dh, how do you write it? One should be ds, right? Okay, that can be second one or the first one, and the other should be what? dp. ds and dp should be the thing. Now you know, with the ds, with the s it will be t, and with the p it will be what? v, right? So t ds, right? t ds and v dp. See, t ds, t is here, and v dp. Can't you see that t in t ds, t is in the top and v is in the top. So both t ds term and v dp term, that will be what? Both positive. So plus. See, why? What happened with the previous one? What happened with the previous one? The term with the p was negative. Okay, either you can remember the term with the p is negative because it is in the bottom. Similarly, the term with the s will be negative because that is also in the bottom. Or you remember these arrows. Okay, whatever it is. Similarly, you try to write the other equations as well. So you can write similarly dA is equal to, just look at these are all repetition of anything will help you to memorize it. dA, how do you, this is dA. So what are the variables first? One is dV and other is what? dt. dV and dt are the variables. Now you have to write its coefficient as the conjugate. What is the conjugate? P is the conjugate. What is the conjugate of T? S is the conjugate. Now you look at P and S. Both P and S are in the bottom of the thing, so both the terms should be minus. Is it not easy? Similarly, finally, what you are left with? You are left with dg. Just look at dg. So what are the natural variables? T and P are the natural variables. So I will be writing dt and dp. Whatever order, doesn't matter. So what is the conjugate variable of T? That is S. And what is the conjugate variable of P? That is V. Right? Now you look at that. See, S is in the bottom, so that should be minus. Okay, whereas V, the variable V, so not the variable, V is the coefficient, V is in the top, so that should be what? A plus. That should be a plus here. So all the four. Now once you get this equation, can't you directly write the Maxwell relation by using your exact nature, dou m by, okay, dou y is equal to dou n by dou x, whatever it is, you can just write all the maximums. Okay, so this is the technique that is usually universally adopted, but what I feel is that rather than this technique, by repeated experience and by recalling what I have already told you, you can easily remember. these four Maxwell's equations and the related thermodynamic equations. Okay, so it's up to you. I leave it to you. The thing is that at the end of the day, you should be able to write all these equations and recall all these equations without a single error, and that is an essential thing for us to discuss further in in thermodynamics. And I will be using these equations repeatedly in the coming topics, where we'll be discussing application of Maxwell's relations. So see that soon after this sessions, you take your own time, take pen and paper, practice it, and be confident that you will be able to reproduce it within 1 or 2 minutes. That's what I depend. Or maximum 5 minutes. Within maximum 5 minutes, you should be able to write all the Maxwell's equations and related all equations without a single error. Practice it, and we will meet with the application of Maxwell's equations in the coming session. Thank you.